Today, we're diving into two fresh papers that push AI beyond static prediction and into embodied action. First, Qwen-VLA from the Qwen team at Qwen shows how a single foundation model can unify vision, language, and robot control across manipulation, navigation, and even human motion. Then, from Zhejiang University, Where to Look asks whether foundation models like Qwen and Gemini can actively explore a room and hit a target viewpoint exactly. It's a fascinating look at where embodied intelligence is headed next. Let's explore the first paper, Qwen-VLA Unifying Vision Language Action Modeling Across Tasks, Environments, and Robot Embodiments. Qwen-VLA from the Qwen team at Qwen presents a single vision language action foundation model that unifies manipulation, vision language navigation, egocentric human motion, and trajectory prediction across robot embodiments. Built on the Qwen 3.5.4b multimodal backbone, it adds a 1.1.5b parameter DIT style flow matching action decoder that generates continuous action chunks with a few Euler steps, while embodiment-aware prompts specify robot platform, arm configuration, control frequency, and horizon so one model can handle heterogeneous control conventions without separate heads. The core novelty is a staged training recipe. Text-to-action pre-training teaches the decoder to reconstruct full trajectories from language alone. Continued pre-training grounds it with images. Supervised fine-tuning aligns downstream tasks. And PPO-based reinforcement learning on sparse success rewards further improves closed-loop control. Training uses a large mixed corpus dominated by real and simulated robot manipulation trajectories, plus 6% egocentric human data, 7.5% navigation data, and curated vision-language supervision. The authors also introduce 359,848 synthetic VLA trajectories and 7.2 million language-only simulated trajectories for action prior learning. On benchmarks, Qwen-VLA Instruct reaches 97.9% on Libero, 73.7% on Simpler Widow X, 86.1%, 87.2% on RoboTwin Easy, Hard, 69% Oracle success on R2R, 59.6% success on RxR, 76.9% average out-of-distribution success on real Aloha experiments, and 26.6% zero-shot success on Domino dynamic manipulation, often beating specialist policies such as Pi 0.5, GR null null T N in.ses, and star VLA. The paper's main claim is that embodied intelligence can be scaled like multimodal pre-training if actions are treated as a shared generative prediction problem rather than isolated robot-specific policies. Let's explore the second paper, Where to Look and Foundation Models Reach a Target Viewpoint Through Active Exploration. Where to Look introduces Target Viewpoint Reproduction, or TVR, a closed-loop embodied task where a multimodal foundation model must move in a 3D indoor simulator until its egocentric camera exactly matches a target image. The authors from Zhejiang University build TVR bench on AI2, Thor, and ProcThor 10K, spanning 500 evaluation tasks across single-room and multi-room scenes with an exact pose matching criterion on a 0.25 m and 45 degrees, 30 degrees action grid. Evaluation shows a large human gap. The strongest open-source model, Qwen 3.5.27b, reaches 7.8% success. The best closed-source model, Gemini 3.1 Pro, reaches 12%, while humans score 93% on a matched subset. The failure analysis is precise. Models over-rotate, rarely issue, stop correctly, and struggle most with body translation, not just visual matching. A unified post-training study finds that supervised fine-tuning on expert visual action trajectories is the key improvement, lifting Qwen 3.5.9b to 50.8% success. Adding trajectory-level multi-turn GRPO on live simulator rollouts nudges this to 51.4%, mainly improving multi-room navigation, whereas chain-of-thought supervision and single-turn GRPO actually degrade closed-loop performance. The paper argues that active spatial intelligence requires learning perception to action mappings over full trajectories, not isolated per-step action prediction. That's a wrap on today's AI paper highlights. Thanks for watching.